thank you for introduction. How about this slide? Is that good?
Yes, it is. We can see it. Yes.
Okay,
Perfect.
thank you very much. Okay, I'm deeply grateful to have been invited by Libel, and they're very interesting talk from the Dr. Arnold, and also Dr. Wilkes is very similar to my research, and I want to use that kind of the method to our lab. And today, I want to talk about in situ observation of the quantum dot using EasyCurve in our lab. I want to introduce the case, which actual using case in our lab. Okay, first of all, I want to introduce the quantum dots and quantum dot lasers. Quantum dot is nanoscale semiconductor structures with unique quantum properties, and its size is smaller than the coronavirus and is around the 20 to 50 nanometers. And using this quantum dot to the semiconductor laser, the quantum dot laser shows the high efficiency light emission, high temperature operation up to 20 degrees Celsius operation, and temperature insensitivity operation, and also low power consumption, high operation, and it also have crystallographic insensitivity. And Stransky-Krasnov cross mode is commonly used for the formation of this kind of quantum dots. This SK gross mode is a fundamental gross mode in thin film deposition, and it's characterized by layer plus island glass. First, we supply the film material to substrate. First, the two-dimensional wetting layer is grown on the top, and then the islands grow from the grow beyond the critical thickness. It's a self-assembled pattern technique for the growth of the quantum dots. And the next is the advantage of the using EasyCurve in quantum dot growth. That allows the real-time monitoring of stress and strain that verify the quantum dot formation mechanism based on stress distribution that enables immediate detection of subtle stress variation during growth, and that confirms strain compensation effects in quantum dot stacking. And that provides real-time reference data for replicating optimal quantum dot conditions and controlling quantum dot size and density. And then they're using this EasyCurve with the another in situ techniques, we can understand deeply to understand the quantum dot growth mechanism and also the capping mechanism. Okay, this is our MB system. We use the Libel Compact 21T system, and we use the arsenic valve cell, the back 500, and dual filament K cells ABN and ABI cells was used for group 3 materials, and bandit temperature measurement system and read was used, and also each curve was used. And we used the quarter of the 3-inch substrate to grow our samples. Then for the small substrate, we can use the easy curve system and easy curve measurements. Okay, the first case, the SK growth mechanism observation in indium arsenide, gallium arsenide growth. We use the read and MIC easy curve at the same time and observe the indium arsenide, gallium arsenide, SK growth modes. And we measure the step-by-step stress changes and check the change of the stress and the read patterns. This is the growth condition and growth sequence. The anti-gallium arsenide or 1/4 of the 3-inch substrate was used. It outgassed at the 450 degrees Celsius. It transferred to growth chamber, and offside was limit at the 620 degrees Celsius. And then we grow the gallium arsenide purple layer and stop the substrate rotation and check the indium arsenide growth at the 450 degrees Celsius. The growth condition is consider the indium at atoms do not evaporate from the gallium arsenide substrate temperature. And then we observe the read pattern from the one bar zero direction and measure the substrate curvature using the MIC method. Okay, this is the results of our works. First of all, we the lead pattern before the time 0, the number 1, there shows the by 4 streak pattern is come from the gallium arsenide that indicate the smooth gallium arsenide layer. And when the shutter open at the number 2 area, the indium is applied and the curvature is decreased like this. And this time the read patterns transition to the by 3 streak pattern that indicating 2-dimensional growth of the indium wetting layer. And as indium arsenide growth progresses and the total deposition reaches approximate the 1.7 monorayer, the curvature continues to decrease. However, the rate of the decrease, the slope is slowed down, suggesting a reduction in curvature change due to indium arsenide growth. This deposition level corresponds to the crystal thickness known for the indium arsenide quantum dots on gallium arsenide. The read pattern change from the streak to the spotty pattern that's showing the distinct chevron pattern. And that also shows the change of the growth mechanism from the 2-dimension growth to 3-dimension growth. Following completion of the indium arsenide growth and the and closer when the indium shutter, the curvature increase like this, and the reduction in tensile stress induced by the indium arsenide growth. Okay, and then we measure the curvature changes, then with brightness at the same time. The measurement point of the brightness is the indium arsenide 004 diffraction point. At the beginning, when the surface temperature is stable, with the curvature and the width pattern remains stable. As the supply of the indium begins, the formation of the initial two-dimensional wetting layer with thickness of the 1.7 monolayer causes the curvature to decrease sharply, from which stress of the minus 5.00 gigapascal can be deduced using the Stoney equations. At this stage, decrease in the overall brightness of the read pattern region can be observed, which is attributed to the darkening of the gallium arsenide centered 4x4 patterns as indium arsenide grows. As the indium arsenide grows for G and reaches 1.7 monolayer, 3D growth begins and the rate of the curvature decrease slow down. And then during the 3D growth process, which correspond to an indium arsenide quantum dot thickness of the around the 3.0 monorail, the stress due to the indium arsenide growth changed to the 2.3 gigapascals. This stress at the 3.0 monorail is less than half of the absolute value compared to the stress of the two-dimensional growth, indicating the transition in the growth mechanism at this stage. Okay, after the three monorail growth, the peak of the brightness is occur on the top of this graph. The brightness of the reef pattern continues increase and then peak at the end of this tree region, and then start to gradually decrease. At this point is the max indicate the max density of the quantum dots, and then it decreases like this. And at this stage, the peak means the point of the density maximum, and the it transition to the quantum dot coalescence formed on the top of the substrate. After the indium supplied is goes slightly up. Okay, this is when collision, real time and in situ observation of the substrate curvature changes in SK growth of the indium arsenide, gallium arsenide quantum dots using the easy curve. Quantification of stress change occurred during this process, and verification of each stage of SK quantum dot growth through the MIC and read at the same time. And I will introduce the second case, quantum dot and capping layer observation in indium arsenide quantum dot, indium aluminum gallium arsenide on indium phosphide. We use the indium phosphide 001 substrate, and we grow the indium arsenide quantum dots with the indium aluminum gallium arsenide quaternary matrix. And then we have to tuning the wavelengths of the this quantum dot, and then for the our goal is development of the high efficient C-band gain materials. Okay, we grow this kind of structure to find 2.5 nanometer partial capping layer of the indium aluminum gallium arsenide was introduced directly on the top of the indium arsenide quantum dots. Between the quantum dot and indium phosphide substrate, we grow the ternary and the quaternary indium indium aluminum arsenide and indium aluminum gallium arsenide alloys, and we also use this. We use the easy curve for the composition calibration for these ternary and quaternary alloys. Also, first of all, we check the indium gallium arsenide, and then you can see the change of the gallium indium cells temperature from the 794 to 784. The height, the curvature is quite sensitively changing from decrease to increase, and we can luckily check the lattice matching, and then we finally check the composition by using the XRD. Then we check the indium arsenide, indium aluminum arsenide, and indium aluminum gallium arsenide also. Okay, after that, we grow the indium arsenide quantum dot on indium phosphide. Then we can obtain the density of the 5 times 10 to the 10th of the indium arsenide quantum dot. The average height of quantum dot was 4.3 nanometer. Diameter was the 20 nanometer. The elongation in the 1 bar zero direction is suppressed by using a thin gallium arsenide insertion layer and arsenic 2 of this. Okay. After then, we grow the quantum dot stacking layer. In the stacking of the indium arsenide quantum dots on the indium phosphide substrate, the changes in curvature at each depths suppressed like this. When we grow the indium arsenide quantum dot, the curvature decreases like this. However, we grow the low composition, low indium composition in indium aluminum gallium arsenide capping layer, it increased like this. By using this method, it shows there also fulfills its low as strain compensation layer like this. Okay, conclude this case. We are successful tuning the emission wavelength from the S-band to U-band using composition control, the indium arsenide, indium aluminum gallium arsenide partial capping, and indium arsenide quantum bond samples on indium phosphide substrate. And we use easy curve for the composition check, and also we can observe the strain compensation layer and allowing effective as used in SEC in the quantum dot structure.